the current darkness. What is occurring in this precise moment beyond the sun's gaze? The celestial body known as Oumuamua, the third known visitor from origins outside our planetary system, is now concealed behind our star, and Avi's pronouncements resonate with increasing urgency as each hour passes. If a sabbatical is desired, embark before the 29th of October. Who can truly predict the unfolding events? Those pronouncements are no longer distant prophecies. They pertain to the immediate 4 days, to the phenomena transpiring right now at a distance of 135 astronomical units from the Sun. As you process this information, Oumuamua achieved solar conjunction 4 days prior, on the 21st of October, positioning itself precisely opposite our planet relative to our star, rendering it invisible to every observational instrument we possess. And in precisely 4 days, on the 29th of October, it will reach its perihelion, the point of closest approach to the Sun within its orbital path, the instant when 33 gigawatts of solar energy will impact its surface. This is equivalent to 1/3 of the total power output generated by all nuclear power facilities in the United States combined, bombarding an entity that scientists at Harvard posit might not be a comet at all, but rather something of considerably greater import. Before we delve further, if you have been monitoring the Oumuamua narrative and wish to remain informed about the developments during these critical 4 days, kindly activate the like function and subscribe to ensure you do not miss our findings when this entity reappears from behind the Sun in November. For today's presentation, we have incorporated some soothing background melodies. Please convey in the comments section if you find this addition agreeable. Furthermore, share your location, the local time, and your thoughts on whether we are witnessing the dawn of first contact in real time. Distribute this across social media platforms and engage the hype button to foster our community's expansion. Your steadfast support is profoundly appreciated. Let us now examine the factors that render these 4 days so pivotal. The temporal alignment here is not merely unusual, it is statistically improbable to an extraordinary degree. Lowe and his colleagues have determined that the likelihood of Oumuamua reaching perihelion while situated diametrically opposite Earth relative to the Sun, with a solar elongation of no more than 30 degrees, is approximately 7%. While not insurmountable odds in isolation, this represents but a single data point within a series of improbabilities that coalesce into a far more disquieting picture. Consider, for a moment, the essence of a Hohmann transfer. It stands as one of the most ingenious stratagems in orbital mechanics. When a spacecraft attains its maximum velocity, which occurs at the closest proximity to a substantial celestial body like the Sun, any propulsion applied is amplified. The kinetic energy acquired is directly proportional to the velocity at which the thrust is exerted. Engaging your engines when already traversing space at peak speed yields a substantially greater return on investment. This principle underpins the utilization of gravity assists in every interplanetary mission. It is fundamental astronautics and the optimal juncture for a retrograde Hohmann transfer, where deceleration and adherence to solar orbit are paramount over escape into interstellar space, is precisely at perihelion. Now, observe where the situation becomes truly intriguing. Oumuamua is poised to execute this maneuver, assuming it is indeed a maneuver, during the sole interval when terrestrial observatories are incapable of detecting it. The Sun completely obstructs our vision. We are rendered sightless. If an entity intended to effect a covert alteration of its trajectory, to decelerate, to deploy auxiliary craft, or to reorient its course towards planets within the inner solar system, this would represent the opportune moment, and we will remain unaware until its emergence on the opposite side in early November. The energy potential available during this specific window is staggering. 33 gigawatts impacting a surface with a minimum diameter of 5 kilometers. This is not conjecture, it is basic physics. Solar irradiance at 135 astronomical units distributed across that surface area. Should this object possess any form of technological capacity, any means to harness or exploit that energy, perihelion would be the opportune juncture for such an endeavor. It constitutes the sole moment within its entire passage through our solar system when maximum power is accessible. Lowe published on his Medium blog just 3 days ago, on October 22nd, meticulously detailing the rationale behind this moment's significance. He characterizes it as a potential black swan event, an occurrence of low probability with profound consequences. He articulates that, presently, Oumuamua appears most likely to be a natural comet, but the remote possibility of a Hohmann transfer must be seriously contemplated due to its immense ramifications for humankind. These are carefully chosen words from an individual who has experienced media misrepresentation previously, who has been labeled as reckless and attention-seeking by his peers, yet he remains resolute. The International Asteroid Warning Network initiated a monitoring campaign on October 27th. That is 2 days from now. The campaign will extend through January 27th, 2026, entailing 3 months of intensive observation. This is not standard procedure for comets. The IAWN is designed to address potentially hazardous asteroids, entities that might pose an impact risk to Earth. They do not expend resources on every icy visitor originating from beyond the solar system. The fact that Oumuamua is being treated as a planetary defense concern implies significant developments occurring behind closed doors. Somewhere, an entity deems this worthy of the infrastructure we have developed to safeguard civilization from extinction-level impacts. Let us discuss what we are precisely looking for when this entity reappears. If Oumuamua continues on a purely gravitational trajectory, adhering strictly to the predictions of celestial mechanics, it will achieve its closest proximity to Earth on December 19th, at a separation of 269 million kilometers, approximately 1.8 astronomical units. While not an intimate encounter, it is sufficiently close for detailed scrutiny. Subsequently, on March 16th, 2026, it will pass Jupiter at a distance of 54 million kilometers. The Juno spacecraft will be ideally positioned to observe this event. The European Space Agency's JUICE mission will approach within 64 million kilometers on November 4th, mere days after perihelion. These are not pre-planned interactions. They are opportunistic encounters, yet remarkably significant ones. The crucial element is this: if the trajectory undergoes modification, if Oumuamua exhibits any deviation from the path dictated solely by gravity, we will detect it in its orbital parameters. Astronomers will measure its position and velocity as it emerges from behind the Sun and compare these with projections. Any discrepancy, any non-gravitational acceleration, any alteration in its orbit will provide us with an answer. Not definitive proof of extraterrestrial intelligence, perhaps, but confirmation that a force beyond gravity and solar radiation pressure is influencing this object. Furthermore, solar radiation pressure serves only to propel objects away from the Sun. It cannot decelerate them, nor can it facilitate a retrograde Hohmann transfer. If this entity slows its velocity in a manner that retains it within the solar system, rather than propelling it back into interstellar space, no natural explanation currently available can adequately account for it. The research paper, co-authored by Lowe, Adam Hibbert, and Adam Kroll from the Initiative for Interstellar Studies, meticulously outlines the potential scenarios. Titled, "Is the Interstellar Object Oumuamua Alien Technology?" It is not a facetious inquiry, but a rigorous astronomical analysis, employing interplanetary trajectory simulation software to calculate the required delta V for various maneuvers. Should Oumuamua intend to intercept Earth, the optimal arrival window would be between late November and early December of 2025, approximately 6 to 7 weeks from now. The delta V requirement is contingent upon the timing of the propulsive burn. However, if executed at perihelion during the period of solar occlusion, the fuel expenditure would be drastically reduced. Efficiency is paramount when traversing light years. Yet, an alternative scenario presents itself, one that is arguably more unsettling. What if it does not directly intercept Earth? What if the mothership, as Lowe refers to it, continues on its gravitational course and simply dispatches smaller probes? These could be autonomous craft, akin in size to intercontinental ballistic missiles equipped with their own propulsion systems. The delta V necessary to reach inner planets from Oumuamua's current trajectory is surprisingly minimal. Less than 5 kilometers per second for Mars, less than 5 for Venus, and less than 5 for Jupiter, achievable before November. These are velocities attainable with conventional chemical rockets. If the objective were to deploy exploration probes to every significant celestial body within the solar system, this trajectory offers an almost ideal conduit. One could traverse the outer solar system, pass by the inner planets, and be strategically positioned to release payloads with minimal energy expenditure. Contemplate this for a moment. The trajectory Oumuamua is following is not optimized for speed. It is not a direct transit through the solar system and beyond. It is aligned within 5 degrees of the ecliptic plane, the orbital disk of all planets. The probability of such an alignment for a random interstellar object is approximately 0.2%. However, if the intent were to visit planets, to gain access to multiple worlds with minimal maneuvering, an ecliptic-aligned path would be the logical choice, offering a multitude of opportunities. The timing of the Mars flyby adds another layer of complexity. Oumuamua passed within 190 million kilometers of Mars on October 3rd. This is a relatively close approach. Multiple spacecraft orbiting Mars redirected their instruments towards it. NASA's Mars Reconnaissance Orbiter possesses an instrument named HiRISE, the High-Resolution Imaging Science Experiment, capable of capturing images with a pixel resolution of 30 kilometers at that distance, an order of magnitude superior to the finest images obtainable from the Hubble or Keck telescopes. HiRISE successfully imaged Oumuamua during its passage, yet these images have not been publicly disseminated, nor have they been shared in any detailed form even within the scientific community. Lowe has actively requested these images, referencing this in numerous blog posts. NASA's reticence on this specific matter is conspicuously pronounced. In contrast, the European Space Agency has maintained a greater degree of transparency. The ExoMars Trace Gas Orbiter captured images of Oumuamua and subsequently released the data. These frames depict a classic cometary appearance, a diffuse white dot accompanied by a faint tail. Reassuring, perhaps. However, the emission characteristics within the spectroscopic data do not correspond to any known comet. The elemental ratios are anomalous, and the chemical composition deviates from expected patterns. This brings us to the observations from the Keck 2 telescope in Hawaii, published just last week, which indicate that Oumuamua is emitting nickel in ratios to iron that do not occur naturally. On Earth, this specific signature is exclusively observed in industrially manufactured nickel alloys produced via the carbonyl chemical process. Nickel is refined by forming and decomposing nickel carbonyl. This is a process we developed for metallurgy. The authors of the paper posit that this carbonyl process could occur spontaneously near the nucleus of Oumuamua, suggesting that conditions there might intrinsically generate these compounds. However, this explanation necessitates a very precise confluence of circumstances that we have never witnessed in any other comet, including 2I Borisov, the preceding interstellar visitor universally acknowledged as natural. The nickel is concentrated within a region extending outward to an exponential radius of 600 kilometers from the nucleus. Cyanide, another detected emission, extends to 840 kilometers. These represent trace outgassing rates, measured in grams per second rather than kilograms. However, the spatial distribution is peculiar. Why would nickel be more concentrated near the core than cyanide? If both are sublimating from ice, they should exhibit similar patterns dictated by volatility and solar heating. This is not the case. The nickel behaves as if it is part of a structured entity rather than a diffuse coma. Horace Drew, a retired researcher from Australia's Commonwealth Scientific and Industrial Research Organisation, examined the Mars images and unequivocally stated, "It is not a comet." He drew attention to the greenish luminescence visible in enhanced versions of the imagery. This green hue, he argues, is consistent with nickel emissions, and he speculates that extraterrestrial entities might coat their spacecraft with nickel, much as we do. This is a bold assertion from an individual possessing legitimate credentials, even if his perspective falls outside the prevailing scientific consensus. It compels us to question why nature would favor nickel as a coating material, or why an icy body would concentrate this particular metal in its outer layers. The counterargument asserts that we are perceiving what we wish to see. It suggests that comets exhibit considerable diversity, and interstellar comets in particular might possess chemical compositions unknown to us due to their formation in different stellar environments with distinct elemental abundances. It posits that every anomalous characteristic of Oumuamua, from its nickel content to its anti-tail and trajectory, is merely a series of coincidences. Unlikely coincidences, perhaps, but coincidences nonetheless. And to be equitable, this is likely the case. The universe is vast, and unusual occurrences are commonplace. 1 in a million chances arise constantly when one analyzes billions of events. However, the crucial point is this. We are not analyzing billions of events. We are analyzing three interstellar objects detected in recorded human history. One in 2017, which exhibited its own inexplicable non-gravitational acceleration. 2I Borisov in 2019, which presented as and behaved like a typical comet, raising no particular alarm. And now Oumuamua, which is defying all established patterns. When your sample size is 3, and one of them exhibits a pronounced anomaly, attention is warranted. Lowe has devised what he terms the Lowe scale, a ranking system from 0 to 10, indicating the probability of an interstellar object being artificial in origin. Oumuamua currently registers a 4. This is not conclusive proof nor even strong evidence, but it is sufficient to warrant thorough investigation. He explicitly states that this ranking will be adjusted based on observations following perihelion. If Oumuamua continues on a standard trajectory, exhibits typical cometary activity after enduring intense solar heating, and behaves precisely as a dirty snowball should, its ranking will decrease to 2. The anomalies concerning its mass and ecliptic alignment would persist, but they would be viewed as isolated curiosities rather than components of a pattern. Conversely, if its trajectory alters, if non-gravitational accelerations become evident, or if its chemical composition grows more unusual, the ranking will increase. Presently, as you are receiving this, on October 25th, 2025, that object is obscured from view by the Sun. It is nearer to our star than Earth is, traveling at 68 kilometers per second at perihelion. Its surface temperature is experiencing a sharp increase. If it is composed of ice, it is undergoing vigorous sublimation, releasing volatile compounds and generating coma and tail pressure. If it is rocky, it is absorbing more energy than it has in millions of years. And if it is something else entirely, if there is even a shred of validity to the technological hypothesis, then it is executing maneuvers that will determine whether humanity is alone in the cosmos. We will ascertain this in November. The period of solar occlusion will end, and telescopes worldwide will reacquire it. Its trajectory will reveal the narrative. Until then, we remain in darkness, literally. And the question is not whether extraterrestrials are arriving. The question is whether we are observing their arrival and simply do not yet comprehend it. Because if Lowe's assessment holds true, if even half of his propositions possess merit, then the next visitor is not arriving in late November. The next visitor is already present, concealed behind the sun, counting down the moments until it can mobilize. And we have 4 days remaining to contemplate what will transpire when the countdown reaches 0. The activation of the IAWN, the reason for the activation of planetary defense systems. There is a document that requires your attention. It is an editorial notice from the Minor Planet Center, published mere days ago, announcing something that should prompt anyone closely following Oumuamua to take notice. The International Asteroid Warning Network has commenced a specific monitoring campaign for this particular object. The campaign began on November 27th. Apologies, let me correct that. The campaign commences on October 27th, which is 2 days from now, and will continue until January 27th, 2026, comprising 3 months of synchronized global observation, utilizing the infrastructure we have established to prevent extinction-level asteroid impacts. And here is what remains unstated by most. The IAWN does not undertake such actions for comets. Let me be unequivocally clear about the nature of the International Asteroid Warning Network. It is not a mere academic research consortium. It is not a collective of amateur astronomers sharing observational time. The IAWN functions as a planetary defense mechanism instituted under the auspices of the United Nations Committee on the Peaceful Uses of Outer Space. Its sole purpose is to detect, track, and characterize objects that pose an impact hazard to Earth. When the IAWN initiates a formal monitoring campaign, it signifies that an entity, somewhere within the decision-making hierarchy, has classified an object as warranting the allocation of resources typically reserved for potential civilization-ending threats. They do not expend these assets on objects of mere scientific curiosity. They do not deploy planetary defense protocols for comets of interest. Therefore, why Oumuamua? The official justification is that it presents an unparalleled opportunity to study an interstellar object with multiple spacecraft in advantageous positions. JUICE will pass within 64 million kilometers on November 4th. Juno will approach it in proximity to Jupiter in March. The geometric alignment is favorable, promising significant scientific returns that should be leveraged as a target of opportunity. This explanation appears plausible until one considers the case of 2I Borisov, which was also an interstellar comet that traversed our solar system with nearby spacecraft. The IAWN did not activate for Borisov. The Global Defense Network was not mobilized. While astronomers observed it extensively, it was through conventional channels and standard prioritization. Borisov was an object of interest. Oumuamua represents something fundamentally different. The timing of this activation is what causes me to lose sleep. The campaign commences on October 27th, which is 2 days prior to perihelion. They are not awaiting the outcome to initiate their measures. They are positioning assets in advance. This suggests that the decision was based on preliminary data, on the anomalies that were already discernible. The trajectory alignment, its dimensions, the nickel emissions, the anti-tail phenomenon. All of these factors were sufficient to warrant its classification as a potential threat scenario. Not a confirmed threat, but a potential one. And in the realm of planetary defense, potential is sufficient justification. One does not await confirmation when the consequence of error is existential. This is where the situation becomes more complex. The mandate of the IAWN pertains to impact threats. Oumuamua is not on a collision course with Earth. Its closest approach in December will be at a distance of 1.8 astronomical units, a separation greater than the closest distance between Earth and Mars. There is absolutely no possibility of impact. Its trajectory is well defined, and its orbital elements are known with high precision. Unless a dramatic alteration occurs, this object will traverse the inner solar system and then proceed back into interstellar space without approaching us closely. Therefore, why activate protocols designed for impact threats for an object incapable of impacting us? Two possibilities exist, neither of which is comforting. The first is that the IAWN has broadened its definition of a threat to encompass non-impact scenarios. If an object exhibited indications of artificial origin, if there existed even a credible possibility of a technological source, this would constitute a different category of threat. Not kinetic, not a projectile from space, but rather an encounter with intelligence. First contact protocols are ostensibly governed by a distinct bureaucratic framework from asteroid deflection, or at least they are supposed to be. However, the boundaries may be blurring. It is possible that when confronted with something that might be an alien spacecraft, one utilizes whatever tools are readily available. And the tools at our disposal are telescopes primarily oriented towards potentially hazardous celestial bodies. The second possibility is that they possess knowledge that has not been shared with the public, that the complete picture appears different from within the network than it does to external observers. And before dismissing this as speculative conjecture, recall that NASA has yet to release the high-rise images from the Mars Reconnaissance Orbiter. The most detailed photographs of Oumuamua in existence, captured with a pixel resolution of 30 kilometers as it passed Mars on October 3rd, are presumably held in an archive somewhere, and no one outside the agency has seen them in any meaningful capacity. Why? What is contained within those images that necessitates restricted access? Avi has publicly requested these images. He has communicated directly with NASA via email. He has documented this in his blog posts. The absence of a response is noteworthy. And just this past week, in a blog entry dated October 24th, Lowe intensified his rhetoric. The individual is now directly leveling accusations at NASA, suggesting they are concealing crucial findings, while simultaneously commending the European Space Agency for their more forthcoming approach to revelations. These are significant pronouncements, particularly from someone holding such a prominent standing within the scientific establishment. This person is not an obscure online commentator. They are a distinguished professor at Harvard, a former head of the astronomy department, and a past member of the President's Council of Advisors on Science and Technology. Consequently, when such a figure asserts that one spacefaring organization is withholding data while another is transparent, it garners considerable attention. The ESA has, in fact, maintained a relatively open stance. Data from the ExoMars Trace Gas Orbiter has been made public. The imagery captured appears to depict a comet, characterized by a diffuse coma and a faint tail, with nothing overtly indicative of artificial origin. However, spectroscopic examination of this same data reveals emission lines that do not correspond to known cometary compositions. The chemical makeup is atypical, and the elemental abundances are anomalous. Despite these discrepancies, the ESA proceeded with its publication. NASA, in stark contrast, has remained largely reticent. Tom Statler, NASA's principal scientist for small bodies in the solar system, offered a single statement to The Guardian, which read, "It looks like a comet. It does comet things." No further detailed analysis, data release, or engagement with the specific anomalies that Avi Loeb has been meticulously documenting has been forthcoming. This has been presented as little more than a dismissal. It is possible that this represents appropriate scientific caution, and that NASA is deliberately avoiding fueling speculation by addressing every unusual measurement. The agency does face a credibility challenge when it comes to UFOs and extraterrestrial phenomena. Decades of dismissals and debunking have conditioned the public to believe that NASA possesses more information than it chooses to disclose. Whether this perception is entirely justified or not, it represents the prevailing reality. Therefore, when NASA maintains silence on a matter of such high public interest, individuals are prone to filling that void with their own interpretations, and Loeb is providing them with the material to do so. His blog post, dated October 22nd, outlines 8 distinct anomalies that he contends warrant a classification of 4 on his specialized Loeb scale. While some of these have been previously discussed, a comprehensive review of the complete list is warranted, as it forms the basis of the International Asteroid Warning Network's IAWN response, and constitutes the evidentiary foundation that has triggered planetary defense protocols. First, the object's orbital plane is aligned within 5 degrees of the ecliptic, a configuration with a probability of only 0.2%. Second, in July and August, a solar jet or anti-tail was observed. Unlike conventional comets, this phenomenon is not attributable to a perspective illusion. Third, the object's estimated mass is approximately 1 million times greater than that of Oumuamua and 1,000 times larger than Borisov, while moving at a faster velocity than both, a scenario with a probability less than 0.1%. Fourth, its arrival time was finely tuned to bring it within tens of millions of kilometers of Mars, Venus, and Jupiter, yet it remained unobservable from Earth during its perihelion. The probability of this occurring is 0.05%. Fifth, the gaseous plume contains significantly more nickel than iron, a composition more akin to industrially produced alloys, with a nickel-to-cyanide ratio orders of magnitude higher than observed in all known comets, including Borisov. The probability associated with this observation is below 1%. Sixth, the gas plume's composition includes only 4% water by mass, a surprisingly low figure given that water is a primary constituent of familiar comets. Seventh, the object exhibits extreme negative polarization, a phenomenon unprecedented among all known comets, including Borisov, with a probability below 1%. Eighth, its trajectory originates from a direction coincident with the WOW signal, with a deviation of no more than 9 degrees. This last point merits further exploration, as the connection to the WOW signal has largely faded from public memory. In August of 1977, the Big Ear radio telescope at Ohio State University detected a powerful, narrowband radio signal that persisted for 72 seconds. The signal was so unusual, so clearly distinct from natural background noise, that the astronomer on duty inscribed "Wow" in the margins of the printout. The signal emanated from the vicinity of Sagittarius, near the border of that constellation with Ophiuchus. It was never detected again. Despite decades of subsequent observation, no explanation has been found. The most plausible hypothesis remains some form of terrestrial interference or a passing satellite, yet the anomaly persists. The incoming trajectory of Oumuamua's successor, now designated C-2017-U1 2017, when traced backward through space, points towards a region of the sky within 9 degrees of the origin of the WOW signal. 9 degrees represents a substantial area of the celestial sphere. The likelihood of a random interstellar object traversing any given 9-degree patch is approximately 0.6%. While not an impossibility, nor even particularly improbable on its own, when considered in conjunction with the other 7 anomalies, the confluence of coincidences becomes statistically improbable. If one were to multiply these individual probabilities, assuming their independence, the cumulative likelihood would fall below 1 part in 10 quadrillion. the figure Loeb consistently cites, equivalent to 1 in 10 to the 16th power. Of course, these probabilities are not entirely independent. The ecliptic alignment influences flyby geometry, which in turn affects timing and observability. A simple multiplication of these figures would be an oversimplification. However, even with generous allowances for correlated factors, and assuming half of these anomalies stem from a single underlying cause, the odds remain exceedingly low, making lottery winners appear commonplace by comparison. The IAW has reviewed these statistics. They have access to all the data, all the measurements, and all the trajectory analyses. Based on this comprehensive review, they have made a critical decision to activate the network and designate this object as a priority, allocating resources for 3 months of intensive monitoring. This decision was not made in a vacuum. It stems from individuals examining the same evidence and concluding that the possibility, however remote, necessitates a response. The consequences of being incorrect in one direction are negligible. If C-2017 U1-2017 proves to be an unusual comet, and we dedicate 3 months to its close observation, we will have expended some telescope time and gained valuable insights into interstellar chemistry. However, if it turns out to be something else, and we fail to observe it, we risk missing first contact, the most significant event in human history unfolding in real time. A report published by the Brookings Institution, frequently referenced in UFO circles, commissioned by NASA in 1961, examined the implications of discovering extraterrestrial life. One of its conclusions suggested that a public announcement of such a discovery could trigger profound psychological and societal disruption, particularly if the discovery involved artifacts or intelligence rather than simple microbial life. The report proposed that a controlled dissemination of information might be preferable to immediate full disclosure. Whether NASA or any other agency actually adheres to these guidelines remains unknown, but the framework for such a scenario exists. The concept that first contact might be managed rather than openly announced is deeply ingrained in institutional thinking. Therefore, when Loeb accuses NASA of suppressing evidence, he is tapping into a suspicion that has persisted for decades. It is conceivable that there is nothing to conceal, that high-resolution images are simply not particularly compelling, and that their release is subject to bureaucratic procedures that naturally cause delays. Alternatively, it is possible that an examination of these images revealed something that warranted a different course of action. A discreet response, the activation of the IAWN without public explanation, or a monitoring campaign framed as a scientific opportunity rather than a threat assessment. The ambiguity is frustrating, as both interpretations are plausible given the current evidence. What is certain is that, commencing on October 27th, the most advanced asteroid tracking network ever devised by humanity will be continuously focused on C-2017 U1-2017 for a period of 3 months. Every deviation from its predicted trajectory will be meticulously recorded. Every spectroscopic signature will undergo analysis. Every photometric variation will be logged. The Galileo Project observatories, Loeb's privately funded sensor network designed specifically to detect technological signatures, will be conducting parallel observations. Should any anomalous activity occur, such as the deployment of mini-probes, a change in trajectory, or any indication of non-gravitational propulsion, it will be detected. The observational window opens in November when C-2017 U1-2017 emerges from behind the Sun. Initial observations are scheduled from the Jupiter Icy Moons Explorer, JUICE, on November 4th. Subsequently, ground-based telescopes will reacquire the object throughout December. The closest approach to Earth on December 19th is anticipated to be a prime period for observation. This will be followed by an encounter with Jupiter in March, during which the Juno spacecraft will be observing. These three distinct observational windows present three opportunities to definitively characterize the object. The activation of the IAWN underscores the significance of these windows, as what is learned over the next 4 months could provide an answer to the overarching question that has shadowed this narrative. Are we alone, or are we being visited? And if we are being visited, what are the implications? This is precisely what planetary defense is preparing for. Not an impact, not an inert celestial body, but a presence, an entity intelligent enough to navigate here, patient enough to approach gradually, and capable enough to time its arrival during a period when direct observation is impossible. The IAWN's activation is not definitive proof of anything, but rather an indication that a sufficient number of individuals believe the possibility warrants serious consideration. When those responsible for averting extinction-level events deem something worthy of such focused attention, it is prudent for the rest of us to pay heed, as monitoring will commence in 2 days. Perihelion is expected in 4 days, and within 3 weeks, initial answers may begin to emerge. The scholarly dispute between the scientific establishment and Loeb and its broader implications are significant. A blog post published in July by Jason Wright, an astronomer at Penn State University, titled simply AVI and C 2017 U1 2017, offers a stark and direct assessment. This piece can be characterized as one of the most incisive academic critiques published outside of a formal peer review rejection. Wright dispenses with pleasantries, immediately stating that Avi Loeb has cultivated a reputation for proposing and asserting that objects could be alien spacecraft, even in the absence of substantial objective evidence to support such claims. He then proceeds to meticulously dismantle, point by point, every major anomaly that Loeb has highlighted concerning C 2017 U1 2017. This is not a mere professional disagreement over interpretation. It is a direct challenge to what Wright perceives as fundamentally flawed scientific reasoning being disseminated directly to the public, bypassing the conventional channels designed to identify and rectify such errors. Wright's central argument is that Loeb's analysis contains elementary mistakes that any competent planetary scientist would recognize immediately. One key piece of evidence Loeb has presented to argue against C 2017 U1 2017 being a comet is the supposed absence of a coma. This stems from a misunderstanding of how telescope tracking operates. When photographing a moving celestial object like a comet, observers have two primary options. Either track the comet itself, resulting in a sharp image of the object with background stars appearing as streaks, or track the background stars, rendering the comet as a blurred smear across the frame. Loeb appears to have examined images where the telescope was tracking the comet, observing a sharp nucleus without a clearly discernible diffuse coma. Wright explains that this is a predictable outcome. A diffuse coma is not clearly visible when the exposure is optimized to maintain a sharp focus on the nucleus. The coma is not absent, it is simply not emphasized under such imaging conditions. Different observational strategies yield different visual results from the same physical object. Size estimations also present another point of contention. Loeb has asserted that C 2017 U1 2017 possesses a diameter of at least 5 kilometers, possibly larger, making it significantly more massive than previously observed interstellar objects. Wright counters that this size estimate is predicated on the assumption that the object is an asteroid with a low reflectivity, an albedo of around 5%. If, as spectroscopic data increasingly suggests, it is a comet, then it would possess a substantially smaller nucleus surrounded by an extensive coma that contributes to its apparent brightness. Brightness alone, without knowledge of reflectivity, is insufficient to determine size. This is a fundamental concept in astronomy. Brightness is a product of size and reflectivity. One cannot solve for one variable without knowing the other. Loeb, Wright argues, selected assumptions that would maximize the perceived size and proceeded with this conclusion, despite these assumptions not being adequately supported by the available data. Furthermore, the images of C 2017 U1 2017 captured by the Perseverance rover on Mars, which circulated widely in early October, have also become a focal point. Enhanced versions appear to show an elongated, cylindrical object, approximately 4 times longer than it was wide, leading to widespread speculation online about it being a spacecraft. Loeb himself had to step in to debunk this interpretation within his own community. He explained that the apparent elongation was a result of the camera stacking hundreds of exposures over a 10-minute period, while C 2017 U1 2017 moved across the sky, essentially motion blur, not evidence of alien engineering. The crux of Wright's argument here is that if the methodology that leads to the interpretation of cylindrical spacecraft from motion blur is flawed, as Loeb himself concedes, then why should other methodologies employed by Loeb, which also lead to dramatic claims based on imaging artifacts and measurement edge cases, be considered reliable? Wright extends his critique to Loeb's assertions regarding non-gravitational acceleration, trajectory statistics, and even the connection to the wow signal. On every point, he claims to have identified either calculation errors, unwarranted assumptions, or misinterpretations of statistical reasoning. He articulates these criticisms with a measured and careful tone, betraying a profound sense of frustration while striving to maintain a professional demeanor. The tension is palpable within Wright's writing. A direct quotation from Wright's blog states, "Loeb's work and behavior have been perceived as so outrageous in many circles that it essentially goes unrebutted in popular forums by those who are in the best position to explain what exactly is wrong about it. This is a damning indictment." Wright suggests that planetary scientists, the experts who dedicate their careers to studying comets and asteroids, have largely abandoned the effort to publicly correct Loeb, deeming it an exhausting and unrewarding task, especially given the public's inclination to disregard such corrections. Stephen Desch from Arizona State University has been even more direct, describing Loeb's work as sloppy and accusing him of circumventing the peer review process to disseminate conspiracy theories directly to the public. This is not merely academic criticism, it is an accusation of scientific misconduct. The peer review system exists to identify errors, compel researchers to justify their methodologies, and ensure that claims are substantiated before they reach the media. Circumventing this process by publishing directly to blogs, issuing press releases, and granting interviews constitutes an end run around the essential quality control mechanisms of science. Loeb is unequivocally engaged in this practice. His posts on Medium frequently precede the submission of formal papers, and his interviews contain claims that are not present in any published work. He leverages his Harvard affiliation to lend weight to speculations that would likely not withstand formal scrutiny. However, a crucial consideration arises. Errors in methodology do not automatically invalidate conclusions. Loeb's calculations may indeed be imprecise, his statistical reasoning questionable, and his understanding of cometary imaging incomplete. All of these points could be valid, yet C 2017 U1 2017 could still exhibit anomalous characteristics. The academic conflict between Wright and Loeb is not fundamentally about the object itself, but rather about the process of scientific inquiry and communication. It concerns how scientific uncertainty should be conveyed and the responsibilities that accompany public platforms. Wright contends that Loeb is undermining the credibility of the field by making sensational claims based on tenuous evidence. Loeb, conversely, believes that Wright and his colleagues are so entrenched in conventional explanations that they instinctively dismiss anything that challenges their established paradigms. A third group is observing this conflict with keen interest: the general public. These are individuals who are not astronomers, who lack access to telescopes or orbital mechanics software, and who are attempting to discern the truth amidst conflicting expert opinions. When Wright asserts that Loeb is incorrect, and Loeb maintains that Wright is exhibiting closed-mindedness, what is a reasonable person expected to conclude? Most individuals are not equipped to evaluate the technical arguments. They cannot independently verify trajectory statistics or confirm spectroscopic calibration procedures. Consequently, they resort to heuristics, attempting to determine who appears more credible, who has more to lose from being mistaken, and who is motivated by genuine scientific curiosity versus a desire for attention. Loeb's responses to his critics have been both fascinating and, at times, troubling. In a recent blog post, he drew an analogy between himself and a Jewish child prisoner in the Terezin concentration camp who depicted idealized visions of a better world instead of the harsh reality of his imprisonment. He suggested that he and others who envision a world superior to Earth might guide humanity towards a promised land through encounters with extraterrestrials. This comparison, which invoked imagery of the Holocaust to portray himself as a persecuted visionary, was widely perceived as profoundly inappropriate. While drawing parallels to Galileo's struggle against academic dogma is one thing, invoking the systematic murder of 6 million people as an analogy for academic criticism represents a significant overreach. However, this comparison also offers insight into Loeb's perception of the current moment. He genuinely believes he stands on the precipice of a historical paradigm shift, that the scientific establishment is overly conservative, risk-averse, and too committed to conventional wisdom. He posits that someone must be willing to bear reputational damage to advance ideas that, while potentially incorrect, warrant consideration. In an abstract sense, he may have a point. Science can indeed suffer from conservatism, with paradigm shifts frequently met with resistance and outsider ideas sometimes dismissed too readily. The critical question is whether C-2017 U1-2017 truly represents such a paradigm-shifting event or serves as a case study illustrating the importance of the peer review process. Betting markets, which offer a peculiar yet surprisingly accurate barometer of collective sentiment, currently place the odds at 75% for a natural comet and 25% for alien technology. These are not scientific probabilities, but rather aggregated human judgments influenced by confidence and financial stakes. Nevertheless, they reflect the current state of public discourse. 3/4 of individuals willing to wager believe it is a comet, while 1/4 finds merit in Loeb's claims. This indicates a lack of consensus and highlights a profound, real-time uncertainty. Chris Lintott from Oxford University has described Loeb's hypothesis as nonsense on stilts, a phrase with historical resonance, originating from the utilitarian philosopher Jeremy Bentham's critique of natural rights theory. Nonsense on stilts implies an idea so fundamentally absurd that it transcends mere incorrectness and occupies a category of its own. Lintott is not simply suggesting Loeb is mistaken. He is arguing that the entire theoretical framework is flawed from its inception, and that it is impossible to logically arrive at the conclusion of alien spacecraft from the available evidence, regardless of how it is interpreted. And yet, the IAWN has been activated, NASA is observing, the Galileo project is mobilized, and ESA is allocating JUICE observation time. Despite the extensive academic pushback and criticism of Loeb's methodologies, these institutions are responding as if the possibility is genuine. This might be attributed to prudent practice, risk management, or perhaps political pressure exerted by those who have read the headlines and demand action. Alternatively, it is possible that, notwithstanding the flawed analysis and methodological issues, there is sufficient circumstantial evidence to warrant a thorough investigation to definitively rule out any underlying truth. Daryl Seligman from Michigan State University, one of the primary authors of the paper that initially characterized C 2017 U1 2017 as an interstellar comet, has attempted to adopt a mediating stance. He emphasizes that this is only the third such interstellar comet ever studied, and that planetary scientists are exceptionally eager to learn about the characteristics of comets from other solar systems. This perspective serves as a deflection, reframing the discussion toward legitimate scientific inquiry and away from speculative alien hypotheses. However, it is also true that even if C 2017 U1 2017 is entirely natural, it carries invaluable information about planet formation in another star system. Its chemical composition can reveal the types of volatiles present in that distant protoplanetary disk, while its trajectory can shed light on the dynamics that led to its ejection. There is substantial scientific value in this object that does not rely on speculation about advanced technology. The academic debate is significant because it will shape future actions. If Loeb's critics prevail in the public discourse and a consensus solidifies around a natural explanation, funding priorities will shift, resources will be reallocated, and the sense of urgency will diminish. C 2017 U1 2017 will then be relegated to an interesting footnote, a peculiar comet that sparked some controversy, and the scientific community will move on. If Loeb's framing gains traction and the possibility of technological origin remains a consideration within institutional thinking, then vigilance will be maintained and observations will continue beyond the initial scheduled windows. We've initiated subsequent missions, treating the dark forest hypothesis with sufficient seriousness to devise defensive strategies. This leads us to the unspoken concern shared by all, the possibility that both existing explanations are incorrect. What if Wright's assertion that Lowe's specific claims are methodologically unsound is true, and simultaneously, Lowe is right that something genuinely anomalous is occurring? Could the reality be neither a natural celestial body nor an extraterrestrial vessel, but something far stranger, for which we currently lack a conceptual framework? The cosmos has a history of presenting us with unexpected phenomena. Pulsars, for instance, were not part of any theoretical models until their detection. Exoplanets were once mere speculation before we identified thousands. Fast radio bursts appeared without prior prediction. Scientific progress is fueled by encountering phenomena that defy current classifications, compelling us to develop new frameworks to accommodate them. 3i Atlas might be compelling us to construct a new paradigm, whether we desire it or not. The academic disputes are a diversion. Wright and Lowe can endlessly debate methodology. It won't alter the nature of the object itself, only our interpretation of the gathered information. And that information is about to become significantly more abundant. The 4th of November marks the JUICE flyby, followed by the 19th of December, its closest approach to Earth, and the 16th of March, a Juno encounter. These three junctures will provide opportunities to rigorously test every hypothesis, conventional or otherwise. The intellectual conflict will momentarily subside as everyone confronts the same fresh data, revealing whose interpretive framework ultimately aligns. Until then, we are observing two scientific narratives unfold concurrently. There is Wright's approach, characterized by caution and skepticism, demanding exceptional proof for extraordinary assertions, safeguarding the discipline's integrity by resisting speculation. Then there is Lowe's approach, audacious and bold, open to potentially erroneous ideas in the pursuit of revolutionary ones, arguing that when the stakes involve initial contact, the cost of overlooking a genuine phenomenon, false negative, outweighs the risk of misinterpreting a natural occurrence, false positive. Both perspectives are defensible and have historically contributed to scientific advancement in various contexts. Both are now poised to be scrutinized by an object indifferent to their deliberations. In 4 days, perihelion occurs. In 3 weeks, we will witness what emerges. At that point, all the debates, methodological disagreements, and academic prestige battles will pale in significance compared to a single, crucial question. Did the trajectory deviate? Because if it did, right and low can endlessly dissect the minutiae later. We will face far more profound challenges. The protocols for initial contact, contingent on realizing we are not alone. Let me share something that should instill a sense of dread. It's an excerpt from Avi's blog, published a mere 2 weeks ago. To the best of my knowledge, there are no established protocols for responding to the discovery of active extraterrestrial technology in proximity to Earth. This scenario differs markedly from detecting radio signals originating from thousands of light years away. An entity present within our immediate cosmic neighborhood necessitates prompt attention, as it could potentially breach our defenses and pose an immediate threat. Consider this. We have contingency plans for asteroid impacts, solar flares, pandemics, nuclear warfare, and catastrophic climate change. Yet, we lack a plan for the consequences of confirming an alien spacecraft within our solar system, currently close enough to reach Earth within weeks. The Brookings Report from 1961 suggested that the discovery of extraterrestrial artifacts could precipitate profound societal upheaval. It advocated for controlled dissemination of information, careful management of public sentiment, and a phased revelation rather than an abrupt announcement. This was written when SETI was in its infancy, when the concept of detecting alien intelligence was purely theoretical. The proposed protocols presupposed ample time, envisioning a radio signal from distant stars, allowing for deliberation on the appropriate response, the content of communication, and even the decision of whether to reply at all. These protocols are predicated on distance, assuming the discovered entity is sufficiently remote to preclude any immediate danger. Three-Eye Atlas upends all those assumptions. If the trajectory shifts post-perihelion, if we observe evidence of non-gravitational acceleration, or if numerous smaller craft are deployed towards planets in the inner solar system, we will know within days. Not years, not decades, but days. JUICE conducts its flyby on November 4th. Ground-based observatories will reacquire the object in early November. By mid-November, trajectory computations will be sufficiently refined to detect any deviations. If an event occurred during the perihelion blackout, if a maneuver was executed, its orbital elements will reveal it. And then what? The initial question is, who will determine the meaning of this information? Not who gathers the data. That's a clear-cut process involving astronomers operating telescopes and spacecraft teams analyzing telemetry. But who interprets it? Who makes the decisive judgment that this crosses the threshold from an anomaly to something artificial? There exists no international body vested with such authority. The International Asteroid Warning Network, IAWN, can designate something as a potential impact threat, but its purview does not extend to potential contact scenarios. The United Nations has a committee on the peaceful uses of outer space, but its role is advisory, not operational. Individual space agencies, such as NASA or ESA, could render determinations, but these would represent national stances, not a global consensus. What will likely transpire is a period of disarray, with various groups reaching divergent conclusions at different speeds. The Galileo project, Lowe's privately financed network, would probably be the first to assert the presence of technological signatures, given their specific search parameters and less stringent evidential thresholds compared to institutional science. They would disseminate their findings, conduct press conferences, and promote the narrative that confirmation has been achieved. Mainstream astronomy would adopt a more measured stance, requiring multiple independent measurements, extensive peer review, and exhaustive elimination of natural explanations. The temporal gap between these two timelines could span weeks or months. During this interval, the public would be caught in an information conflict between confident assertions and cautious skepticism. Social media would erupt. This is not hyperbole, but a prediction based on current information dissemination patterns. Every amateur astronomer with a telescope would be posting images, every conspiracy theorist would proclaim vindication, and every governmental skeptic would allege cover-ups. The signal-to-noise ratio would be catastrophic. Lost within this cacophony would be the actual data, the genuine observations, the measurements that truly matter. The majority of individuals would be incapable of distinguishing between them, instead adopting narratives based on their preconceptions, their trust in specific sources, or what aligns with their worldview. By the time a scientific consensus, if ever, emerges, public opinion would have already solidified. Governments would face unenviable choices. Should they preempt the narrative and issue an official statement before scientific consensus is established? Should they risk being incorrect, potentially inciting panic over something that ultimately proves to be natural? Or should they remain silent, allowing rumors to fester and risk appearing to withhold information? Both approaches have historical precedents, and both have yielded unfavorable outcomes. The War of the Worlds radio broadcast in 1938 caused widespread panic, despite being clearly fictional, because listeners tuned in late and missed the disclaimer. The Orson Welles effect is undeniable. However, governmental silence during genuine crises, from pandemic responses to intelligence failures, fuels conspiracy theories that are often more detrimental than the truth itself. Let us assume confirmation occurs. Suppose by mid-November, the evidence is sufficiently compelling for major space agencies to issue synchronized statements acknowledging that 3I Atlas exhibits characteristics inconsistent with natural phenomena. What transpires in the initial 24 hours? Markets would undoubtedly plummet. This is not due to a rational assessment of economic impact, but because uncertainty destabilizes markets more rapidly than negative news. Investors would seek refuge in secure assets. Governments would suspend trading to avert complete collapse. Emergency economic measures would be implemented within hours. Religious institutions would confront profound existential questions. The Catholic Church, for instance, has actually been preparing for such an eventuality. Vatican astronomers have publicly stated that the existence of extraterrestrial intelligence would not contradict Catholic theology, positing that God's creation might extend beyond Earth and that alien beings could possess their own divine covenants. Other denominations are less prepared. Evangelical Christianity, particularly in its American iteration, holds significant theological tenets regarding human singularity and Earth's unique position in creation. The confirmation of alien life does not merely challenge these beliefs, it could potentially invalidate them. This would likely result in schisms, rapid theological reinterpretations, or in some instances, outright denial. The psychological ramifications would vary significantly across cultural contexts. Western secular societies might adapt relatively swiftly. The concept of aliens is already prevalent in fiction, entertainment, and speculative science. It would be astonishing but not incomprehensible. Other cultures, especially those where religious cosmology is deeply interwoven with daily existence, would face more arduous adjustments. Furthermore, there are the accelerationists, individuals who would perceive first contact as an opportunity to leapfrog current limitations, access advanced technologies, and resolve Earth's problems with extraterrestrial assistance. They would advocate for engagement, communication attempts, and welcoming gestures. Conversely, they would be opposed by those who view any contact as inherently perilous, who advocate for isolation, and who believe humanity's sole recourse is to conceal itself and hope to evade notice. Military responses would be triggered immediately. This is not predicated on the belief that we could engage an interstellar civilization, but rather that it is the function of militaries to prepare for threat scenarios, regardless of their asymmetry. The Space Force, an entity largely forgotten by the public, would suddenly assume paramount importance within the U.S. military structure. Defense satellites would be retasked for tracking purposes. Ground-based radar networks would be placed on high alert. Missile defense systems, designed for ballistic threats, but theoretically capable of intercepting slow-moving objects in near-Earth space, would be positioned. All of this would likely prove futile if the technological disparity is as significant as anticipated. Nevertheless, these preparations would proceed because inaction is politically untenable. Then there is the question of communication. Should we attempt to transmit messages? If 3i Atlas deploys numerous probes toward Earth, and these probes arrive in late November or early December, should we initiate first contact protocols, radio signals, laser communications, mathematical sequences, prime numbers, the very elements SETI has been developing for decades? The fundamental issue is that these protocols assume a cooperative interaction, presuming the other party desires to communicate. If the dark forest hypothesis holds true, suggesting this is surveillance or reconnaissance preceding a hostile act, then amplifying our presence beyond its current detectability would be tantamount to self-destruction. But how can we differentiate between a probe sent for observation and one intended for our eradication? We cannot. Not without more data, not without some form of reciprocal engagement. And by the time such data becomes available, it may be too late to alter our strategy. Lowe drew a parallel to a blind date, where one hopes for friendliness, but must also guard against the possibility of encountering a serial killer. It is a deliberately provocative analogy, yet it encapsulates the uncertainty. When intentions are unknown and one cannot even ascertain the other party's capabilities, every decision becomes a gamble. Do we advance or retreat? Do we project strength or vulnerability? Do we attempt to appear valuable as potential allies or threatening enough to deter conquest? Game theory provides frameworks for such dilemmas, but they all rely on assumptions about the other player's utility function, assumptions for which we have no basis. Academic institutions would scramble to maintain their relevance. Every university with an astronomy department would launch research initiatives, solicit emergency grants, and convene symposia. The field of astrobiology, previously a somewhat niche area, would experience explosive growth. Linguists would propose xenolinguistics programs, despite lacking any actual examples to study. Philosophers would engage in debates concerning the moral standing of alien intelligence, whether we bear obligations toward them, and whether they possess rights within human ethical frameworks. It would represent an intellectual gold rush, with everyone vying to stake claims in a field that, just a week prior, barely existed in any meaningful sense. The technological aspect would dominate practical discussions. If this is a spacecraft capable of interstellar travel, it possesses power systems, propulsion technology, material science, and computing capabilities that far surpass our achievements. Would reverse engineering become the paramount objective? Would we attempt to recover fragments, to study the probes should they land or crash? Or would the technological chasm be so vast that attempting to comprehend it would be akin to presenting a smartphone to an individual from the Bronze Age? They might recognize its sophistication and even discern its functionality, but the underlying principles, the physics and engineering, would remain entirely incomprehensible. We might find ourselves in precisely the same predicament. And then there is the issue of potential colonization, a matter no one wishes to articulate. If 3i Atlas is indeed artificial, a mothership, how many others are there? Is this a singular probe from one civilization engaged in random exploration? Or is it part of a network, a routine survey route, one among thousands or millions of similar objects distributed across the galaxy? If the latter scenario is true, then we are not facing initial contact. We are realizing that we have always resided in a populated cosmic neighborhood and simply failed to notice. This fundamentally alters our understanding of our future, our expansion into space, and the very scope of what is possible and permissible. If the galaxy is already claimed, already partitioned and governed by powers far older than our own, then humanity's cosmic trajectory might be considerably more circumscribed than we have envisioned. The optimistic scenario posits benevolence. It suggests that contact would usher in technological transfer, medical advancements, solutions to climate change and energy scarcity, and answers to fundamental physics questions that have long eluded us. It proposes that the motivation for alien visitation would be curiosity, scientific interest, or perhaps a form of cosmic altruism, where advanced civilizations assist younger ones in navigating the perilous transition from technological capability to wisdom. The Drake equation suggests that intelligent life is rare. If one has overcome the odds to develop, perhaps there is an inherent responsibility to aid others in doing the same. This is an optimistic outlook, yet it is entirely unsubstantiated by evidence. We have a single example of intelligent life, ourselves, and we are not particularly altruistic towards other species on our own planet. The fearful scenario involves resource extraction, not necessarily our resources directly, but the sun's energy, the metals of the asteroid belt, or planetary real estate. Earth might hold intrinsic value, or it might simply be an obstacle. Terraforming spans centuries, but if one possesses the patience for interstellar journeys, one is already thinking in such temporal scales. A probe assessing habitability, evaluating planetary resources, cataloging defenses. This is precisely what one would dispatch before committing to a full-scale operation. And if the assessment concludes that the local inhabitants are primitive, fragmented, barely capable of spacefaring, and unable to mount a meaningful resistance, then the report would be sent back, and the fleet would advance. This represents the nightmare scenario, not encountering exploration, but the advanced scouts of colonization, and we would not realize the distinction until it was far too late to influence the outcome. These are no longer theoretical exercises. If November brings confirmation, these questions will become immediately pressing. Every government, every institution, every influential individual will need to establish a position on communication, defense, disclosure, and preparedness. And we have 4 days to hope we never need to address them, or 4 days to begin preparing for the most significant transition in human history. Because if this is real, if 3 Atlas is artificial, then all subsequent events will be measured against the benchmarks of before contact and after contact. And we are currently living through the final moments of before, counting down to a perihelion that could fundamentally redefine what it means to be human in this universe. The mothership hypothesis. What might be deployed during perihelion? There is a calculation within the Hibid, Cra, and Low paper that most readers skimmed over, buried as it is within complex trajectory analysis. Yet it is the very calculation that should be keeping us awake at night. If 3 Atlas is a mothership carrying smaller craft designed for inner solar system exploration, then the most advantageous window for deployment is during perihelion, and the optimal arrival period for these smaller vessels to reach Earth is between late November and early December of 2025, not years from now, not decades, but 6 to 8 weeks from the present. The required velocity changes, known as delta V, are surprisingly modest. Less than 5 kilometers per second are needed to reach Earth from 3I Atlas's trajectory. If the thrust occurs at perihelion, this velocity is comparable to that of an intercontinental ballistic missile. We have possessed this technology since the 1960s. If they are capable of interstellar travel, they can certainly achieve 5 kilometers per second. Let us contemplate the actual nature of these miniature probes, not in the fantastical terms of science fiction with crews and weaponry, but rather in the practical context of reconnaissance. They would likely be small, autonomous, heavily shielded against radiation, possessing just enough propulsion for trajectory adjustments and sufficient sensors to gather data, perhaps the size of a car or even smaller. Mass limitations for interstellar travel are exceptionally severe. Every kilogram incurs an exponential cost in terms of fuel or time or both. One does not transport bulk. One sends the minimum viable payload capable of accomplishing the mission. For reconnaissance, this entails instruments, computers, and just enough propellant for localized maneuvering. Humans, or their equivalent, would remain aboard the mothership. The probes would proceed ahead. The paper calculates that if 3 Atlas intended to intercept Earth, the arrival date that minimizes delta V falls within the late November window, specifically between late November and early December. This is not coincidental. It is dictated by orbital mechanics. The relative positions of Earth and 3I Atlas after perihelion, the phase angles, and the relative velocities all converge to make this particular window optimal. Before this time, more propellant would be required. After this time, more propellant would be necessary. There exists a sweet spot, and it opens in approximately 5 weeks. If probes were deployed on October 29th and initiated their engines to decelerate and reorient towards Earth, they would arrive precisely within that window. We would not detect their approach. Objects of such small size, not emitting light, simply coasting on ballistic trajectories with intermittent course corrections, would remain invisible to our detection systems until they were remarkably close, perhaps hours away, possibly less. What would be their actions? The benign scenario involves observation, a flyby of Earth, scanning the planet, analyzing atmospheric composition, mapping surface features, cataloging electromagnetic emissions, and detecting signatures of industrial civilization. This is precisely what we would do if we dispatched probes to another inhabited world. Gather data before making decisions about further contact. One assesses technological sophistication, social organization, potential threats, and opportunities for cooperation. Voyager carried a golden record with sounds and images of Earth, a message in a bottle for any potential discoverer. This exemplifies benign reconnaissance, curiosity expressed through instrumentation. The concerning scenario is markedly different. The same instruments, the same data collection, but the objective is not scientific. It is strategic. One maps infrastructure, identifies critical nexus points, inventories defenses, and measures response capabilities. One ascertains the locations of power grids, communication hubs, and military installations, not with the immediate intention of utilizing this information, but to have the assessment completed should it ever become necessary. Intelligence gathering, much like that conducted by orbital surveillance platforms and unmanned reconnaissance craft, often mirrors the preparatory efforts for unforeseen eventualities. The distinction between data amassed for innocuous reasons and that collected for strategic objectives is imperceptible from the methodology alone. It is only discernible by subsequent actions. There exists a third, more peculiar possibility. The exploratory vessels are not here to scrutinize humanity at all. Their purpose may be to observe something entirely different, with our presence being merely incidental. Perhaps the primary subject of interest is Earth's biosphere, rather than human civilization. It is conceivable that there is an ongoing examination of life's evolutionary progression across various worlds, with our species serving as a single data point within an extended research initiative. Alternatively, these craft might be periodic visitors, having frequented our celestial vicinity for millennia or even eons, with our recent detection stemming from our own technological advancements, finally reaching a point where such observations are possible. This realization would cast us as latecomers to our own discovery, acknowledging surveillance that commenced long before our awareness. Such a prospect is both humbling and disquieting in equal measure. The research paper indicates that a single vessel, designated 3I Atlas, possesses the capacity to deploy exploratory units towards multiple destinations. Mars experienced a close flyby in October, occurring within a range of 190 million kilometers. Venus is slated for a similar encounter in the forthcoming months, and Jupiter is positioned on a trajectory for an encounter scheduled for March. If the overarching objective is to conduct a comprehensive survey of the solar system, then traversing paths that encompass all significant celestial bodies of interest represents an efficient strategy. This approach prioritizes broad coverage rather than singular planetary focus. From a strategic viewpoint, this logic is sound. Why undertake the arduous journey to investigate a solitary world when multiple bodies can be examined? The sheer magnitude of the infrastructural investment required for interstellar transit renders the marginal cost of supplementary observations virtually negligible once arrival is achieved. Consequently, probes are dispatched to every accessible location. Now, let us consider the implications should these probes reach Earth and be detected. This scenario pertains not to their landing or impact, but to their inbound trajectory, affording us hours or even days of forewarning. Would we attempt an interception? The technical means are available. We possess missiles capable of reaching low Earth orbit and anti-satellite weaponry that could, in principle, neutralize an approaching object if its flight path were known with sufficient precision. However, the crucial question remains: should we? If these are investigative units from a civilization capable of interstellar travel, their destruction could be construed as an act of aggression. This decision might represent the most calamitous choice humanity could ever make, transforming a potential first contact into an outright conflict due to a defensive reaction to something that posed no actual threat. Conversely, permitting unidentified craft to enter our airspace or orbital domain without challenge establishes a precedent of inaction. It signals an inability or unwillingness to safeguard ourselves. Game theory principles suggest that demonstrating capability, even if unused, influences perceptions and treatment by others. A civilization possessing the capacity for probe interception is perceived differently from one that lacks it, irrespective of whether such an interception would ultimately prove futile against a more advanced adversary. The demonstration itself holds significance. Nevertheless, these are complex decisions that would require resolution within hours, under conditions of profound uncertainty, by individuals unprepared for such a quantum. The potential ramifications of an incorrect decision are immeasurable. The issue of communication resurfaces here. Should probes arrive, what actions would we take? Would we transmit messages, radio broadcasts, laser signals, or sequences of mathematical principles in an attempt to establish communicative protocols? The arguments in favor are compelling. This is precisely the scenario SETI has been preparing for and represents the initial step in any contact paradigm. The counter-arguments align with the dark forest hypothesis. If their awareness of our existence is nascent or uncertain regarding our significance, broadcasting our presence could prove to be our ultimate undoing. However, if they dispatched probes specifically targeting Earth, then our existence is already known. In such a case, the decision to broadcast would not be one of revelation, but an attempt to shape the nature of the encounter from its inception. It would be an endeavor to convey cooperation, communicative intent, and a desire for peaceful engagement. Whether such an endeavor would be beneficial or detrimental hinges entirely on their intentions, which we are currently unable to ascertain. An engineering consideration warrants attention: the power demands of these miniature probes. If they rely on chemical propulsion, akin to conventional rockets, The fuel mass required for the necessary velocity changes would be substantial, making them larger, heavier, and more challenging to deploy in vast numbers. Conversely, if they employ more advanced propulsion systems, such as nuclear thermal, ion drives, fusion, or even technologies beyond our current understanding of physics, the mass ratios would improve dramatically, allowing for smaller, lighter probes and the deployment of a greater quantity. The sheer size of the 3 Atlas vessel, estimated at a minimum of 33 billion tons based on trajectory analysis, suggests it could carry hundreds or even thousands of diminutive probes without a significant impact on its mass budget. Such a primary vessel would not necessitate landing or atmospheric entry. Its sole function would be to transport and release the smaller units at opportune moments. Lowe's blog post, dated October 22nd, elaborates on this precise scenario. If 3 Atlas is indeed a colossal mothership, it is likely to continue along its original gravitational path, eventually departing the solar system. In this context, the Obath maneuver could be applicable to the miniature probes released towards solar system planets during its perihelion pass. This strategy offers strategic advantages. The mothership remains secure, maintaining its outbound trajectory and avoiding entanglement within a system where it could potentially be trapped or targeted. The probes assume the risks, gather the data, and their loss or destruction would be considered acceptable. The mothership, regardless, would be capable of transmitting its findings. Where might probes designed for surface exploration potentially land? It is improbable that they would target urban centers, given the heightened risk of immediate detection and potential confrontation. Remote regions, areas with minimal human presence, would be more conducive to their operation without interference, while still allowing for distant observation. High-altitude locations provide advantageous sight lines for observation. Arid desert environments offer reduced meteorological interference and stable ground conditions for instrumentation. Arctic regions, while isolated, present scientific interest for climate studies. The ocean floor represents another viable option, vast and largely uncharted, providing an ideal cover for sensor deployment. Without a specific search effort, their discovery would be improbable, and even then, the search area is astronomically immense. Alternatively, they might forego landing altogether, maintaining orbits sufficiently high to circumvent atmospheric drag while remaining low enough for detailed observation. While geostationary orbit is densely populated with our satellites, there is still available space. Lower orbits present challenges in maintaining stability without maneuvering fuel, but they afford superior resolution. A distributed network of probes across multiple orbital planes could achieve comprehensive Earth coverage with a comparatively small number of assets. Furthermore, if these probes possess stealth capabilities, emitting no signals, reflecting minimal light, and generally remaining inconspicuous, they might evade detection amidst the myriad pieces of space debris and defunct satellites already present. The timeline is a critical factor. If deployment occurred at perihelion on October 29th, and the transit time to Earth is estimated at 4 to 6 weeks, then their arrival would be anticipated in early December, around December 19th. This date coincides with 3 Atlas's closest approach to Earth, occurring at a distance of 1.8 astronomical units. Such synchronicity is indicative of meticulous planning rather than coincidence. The mothership would pass at a safe distance while the probes converge on their target. This scenario allows for simultaneous observation from 2 distinct vantage points: the proximate probes providing granular data, and the distant mothership offering contextual information and serving as a communication relay. This represents an elegant mission design for coordinating reconnaissance across interplanetary distances. What measures could we realistically employ to detect inbound probes? With our current infrastructure, our options are quite limited. Our space surveillance network is primarily designed to track objects within Earth's orbit and, to some extent, cislunar space. Objects approaching from interplanetary regions, especially smaller units lacking active transponders, would only become visible when they are exceptionally close, potentially within the Moon's orbit. At that juncture, we would have a maximum of mere hours to react. Enhancing detection capabilities, deploying novel sensor systems, and establishing more comprehensive coverage would necessitate months or even years. If probes are expected in December, we will not be adequately prepared. Our awareness of their presence would likely mirror how we discover most new phenomena, when they have already arrived and an anomaly is noticed. The psychological impact of confirmed probe arrival would differ significantly from the detection of a mothership. The mothership, being distant and abstract, lacks an immediate sense of presence. Probes in orbit or on the surface, however, possess a tangible and visceral quality. They are physically here, in close proximity, potentially observing us directly. The resulting paranoia would be extreme. Every unusual occurrence would be interpreted as probe activity. Every unexplained aerial luminescence, every peculiar electromagnetic signal, every anomaly in satellite behavior would be construed as evidence or potential evidence. Conspiracy theories surrounding UFOs, which have circulated for decades, would suddenly gain a concrete focal point. The disconcerting aspect is that some of these theories might prove accurate, rendering the task of discerning genuine signals from background noise virtually insurmountable. We must contemplate the possibility of no event occurring. Perihelion passes without incident, November arrives, and observations reveal normal cometary behavior, with no detectable trajectory alterations, no probe deployments, and no anomalies beyond those already catalogued. Would this invalidate the technological hypothesis? Or could it signify a level of technological sophistication far exceeding our current comprehension, enabling maneuvers undetectable to us or operating on timescales beyond our observational capacity? If the mothership establishes a stable position in Jupiter's orbit in March, remaining out of the way yet demonstrably present, it would not constitute an immediate threat, but would represent a permanent alteration of our cosmic landscape. We would be compelled to coexist with the knowledge that an artificial entity is observing, awaiting, and undertaking whatever purpose it was designed for. It is plausible that we would never gain further insight. The ambiguity could persist for years, decades, or even generations. No contact, no communication, merely a persistent presence, the stark realization of being observed. This scenario might prove more unsettling than direct contact. At least with contact, there is the potential for answers. Observation, conversely, yields an escalating series of questions without resolution. These unanswered questions, in turn, would inevitably shape our behavior. Would we alter our actions, conscious of being watched? Would we strive to showcase our most admirable qualities? Or would we choose to ignore their presence, continuing our lives as usual, refusing to perform for unseen arbiters? These are not abstract philosophical inquiries. Should probes indeed arrive, they transform into practical considerations dictating how humanity conducts itself under alien scrutiny. We have a mere 5 weeks to determine if we require answers. What makes the year 2025 particularly significant? If 3 Atlas is artificial, or if it operates on behalf of an intelligent entity, then the lingering question that troubles me is not whether it is here, but why. Interstellar travel, by its very nature, is time-intensive. Even at the velocity of 68 kilometers per second, which 3I Atlas maintains at perihelion, traversing the distances between neighboring star systems would require tens of thousands of years. Journeys from more distant locations would extend into hundreds of thousands of years. The planning horizon for an interstellar mission is of a geological scale. Such an undertaking is not initiated on a whim, but rather based on a reasoned expectation that the destination will justify the investment upon arrival. Therefore, what has transpired concerning Earth, humanity, or this specific juncture in our development that would render us of interest now? In astrobiology, there is a concept known as the technosignature window. This refers to the temporal period during which a civilization is detectable from interstellar distances. Prior to the advent of industrial technology, Earth presented itself as a typical habitable world. It possessed abundant atmospheric oxygen generated by photosynthesis, liquid water, and a temperature range conducive to life, but nothing that overtly indicated intelligence. We had developed cities, agriculture, and complex societal structures, yet from light years away, these attributes are not discernible through spectral analysis. What is detectable is chlorophyll, methane indicative of biological processes, and other signs of life, though not necessarily intelligent life. This characterized Earth for billions of years. Subsequently, a fundamental shift occurred. One could pinpoint the year 1876 with Alexander Graham Bell's patent for the telephone. While the telephone itself is not directly relevant to alien detection, it marked the genesis of telecommunications, which eventually led to radio and, consequently, to broadcast signals propagating through space at the speed of light. Suddenly, Earth was no longer merely alive. It became acoustically conspicuous. Radio transmissions, television broadcasts, and radar pulses all permeated space, creating an expanding sphere of electromagnetic signals emanating from Earth's center. This sphere now encompasses a radius of approximately 150 light-years. Any civilization situated within this radius, equipped with sufficiently sensitive receivers, could detect our presence, thus inferring the existence of technological activity. However, radio waves are merely one form of signature. Others have emerged more recently. Nuclear weapons testing conducted in the 1940s and 50s generated atmospheric signatures, including isotopic ratios that do not occur naturally in the concentrations we produced. These tests were energetically potent, involving multiple kiloton and megaton detonations that released gamma rays and neutrons into the atmosphere, briefly rendering Earth one of the brightest objects in the solar system across specific wavelengths. Had observers been present with the appropriate instruments focused in our direction, they would have witnessed a planet that had recently mastered nuclear fission and was testing it in the open atmosphere. This constitutes a technosignature, a marker of developmental advancement. Then there is artificial illumination. Satellite imagery from the 1980s onward reveals Earth's night side illuminated by the glow of cities, with billions of lights delineating coastlines and continents. From space, even from nearby vantage points like the Moon, this phenomenon is unmistakable. From interstellar distances, with sufficiently powerful telescopes, it would still be detectable. The light pollution, which we perceive as a problem, also serves as a beacon. It indicates a world with dense populations utilizing substantial amounts of energy after dark, implying electricity generation, infrastructure, and urbanization, all hallmarks of a technological civilization. The composition of our atmosphere has also undergone changes. Carbon dioxide levels have risen sharply, commencing with the Industrial Revolution. However, the acceleration observed in recent decades is unprecedented. Geological records show increases in methane. Nitrogen oxides have also risen. Chlorofluorocarbons, CFCs, have appeared, substances that do not occur naturally. From a distance, analyzing light passing through Earth's atmosphere during transits, and with the correct viewing angle, one would observe chemical fingerprints of industrial activity. This indicates not merely life, but technology operating on a grand scale. This signature has become pronounced only over the past 70 years. Prior to this period, Earth's atmosphere bore a pre-industrial appearance. Therefore, when mapping the galaxy and cataloging worlds that might develop spacefaring civilizations, Earth only became unequivocally technological within recent historical memory. The signals announcing our presence have been propagating outward for approximately a century, extending their reach progressively further each year. If 3 Atlas was launched in response to the detection of these signals, if some civilization perceived our radio bubble, our nuclear testing, or our atmospheric alterations and decided to investigate, the timing aligns. A probe launched a century ago, undertaking a journey of decades, arrives now when the civilization that emitted the signals is, hopefully, still present and perhaps has evolved sufficiently to warrant interest. However, another, more somber possibility exists. Perhaps they are not reacting to our signals. They may be following a predetermined survey route, visiting habitable worlds at intervals to assess their status. Earth might be visited every 100,000 years, or every million years, or some other interval sufficiently long to allow for significant evolutionary changes between visits. On most such occasions, nothing remarkable would be observed. Life would exist, but would not have attained complexity or intelligence. Then, their arrival in 2025 yields a surprise. The hominids have mastered nuclear fission and spaceflight. This renders this visit distinct from previous ones, not because they specifically chose this time, but because our development happens to coincide with their scheduled survey window. We are an incidental finding within their operational timeline, and their response is dictated by what they discover, rather than what they anticipated. A third scenario is predicated on the concept of the Great Filter. This theory posits that somewhere between the emergence of single-celled life and the establishment of a galaxy-spanning civilization, there exists a barrier that most species fail to surmount. This barrier might be the development of multicellular organization, the achievement of technological intelligence, or the successful navigation of a period characterized by the possession of weapons of mass destruction without the requisite wisdom to avoid their use. It is within this last category that we currently find ourselves. Nuclear weapons, biological agents, climatic alteration, and the advancement of artificial intelligence, coupled with synthetic biology, have brought us to a precipice where self-annihilation or fundamental alteration of our trajectory is possible. Moreover, we are progressing through this phase at a pace that outstrips the adaptability of our social institutions. If an advanced civilization were monitoring developing worlds, the Great Filter period would be precisely when they would focus their attention. Prior to this phase, a species is unlikely to be of significant interest, as it is probable that they will succumb to natural catastrophes. After this phase, should they persevere, they become potential peers or at least prospective participants in any existing galactic community. However, during the filter itself, within the narrow window where their fate could diverge in either direction, intervention might prove meaningful, or at least critical assessment becomes imperative. Are these beings on the verge of destroying themselves? Will they achieve stability? Do they require assistance, a warning, or simply observation to witness the outcome? We are currently within that critical window. We have been since 1945, when the Trinity test demonstrated our capacity to split the atom, and we might emerge from it within the next century, one way or another. China's lunar landing on the far side, SpaceX's development of reusable rockets, the deployment of the James Webb Space Telescope, CRISPR gene editing, and the apparent reasoning capabilities of large language models. These are all developments that have occurred within the last decade. The pace of change is exponential. An observer from afar, witnessing a species progress from its first powered flight to landing on its moon in 66 years, and from room-sized computers to pocket-sized supercomputers in 50 years, would recognize this pattern. This represents a civilization in a phase of rapid development. They are inherently unstable and unpredictable, but also on the cusp of becoming significantly more capable. This confluence of factors makes the present moment exceptionally significant in ways that might not have been the case a century ago or might not be a century from now. Furthermore, there is the possibility that the focus is not on us at all, but rather on Earth's position within a broader cosmic framework. The solar system traverses the galaxy, completing an orbit around the galactic center approximately once every 230 million years. We currently reside within a region known as the Orion Spur, a minor arm situated between the major spiral arms. Different sectors of the galaxy exhibit varying stellar densities, metallicities, and concentrations of dust and gas. It is conceivable that 3 Atlas is conducting a survey of this region, visiting multiple star systems, with Earth being but one stop on a much more extensive itinerary. Our status as an inhabited world might render us more intriguing than gas giants and barren rocks, but we are not the primary raison d'être for the mission. Rather, we represent a discovery made during its execution. The connection to the WOW signal introduces another layer of intrigue. This signal was detected in 1977, originating from the direction of Sagittarius. 3 Atlas is approaching from within 9 degrees of that same celestial bearing. If these two phenomena are related, if the signal was transmitted by the entity responsible for launching 3I Atlas, or by 3I Atlas itself while still at a considerable distance, then the timing of events becomes particularly telling. The signal, dispatched in 1977, reached Earth and was detected but not fully understood. 48 years later, the object that sent it arrives. This represents a plausible time frame for a probe traveling at a fraction of the speed of light, not exceptionally fast by science fiction standards, but demonstrably capable. It also suggests that the signal might have served as a warning, an announcement, or a test to gauge our response to any stimulus. We did not respond, merely logging it as an unexplained anomaly and moving on. This inaction may have conveyed something about our readiness for contact. The development of artificial intelligence could be the pivotal factor, not necessarily because AI is inherently perilous, though it might be, but because it signifies a crucial threshold. Once artificial general intelligence is achieved and systems capable of recursive self-improvement and design of superior iterations come into being, superintelligence could be mere months or years away. Such superintelligence would fundamentally alter reality, capable of solving humanly intractable problems, conceiving technologies beyond our grasp, and operating at speeds and scales far exceeding biological cognition. If an extraterrestrial civilization were monitoring for existential risks or species requiring intervention, the development of AI would undoubtedly serve as a stark warning. It would signal an imminent, profound transformation in humanity, necessitating an assessment before such changes render the species unrecognizable. Our own advancements in AI capabilities, loudly proclaimed through research papers, public demonstrations, and commercial applications disseminated via telecommunications that extend into space, would make our progress evident. Any sufficiently advanced listener would be aware of our pursuits and our proximity to this threshold. Should they have undergone a similar transition themselves, possessing first-hand knowledge of its implications, they might hold strong convictions regarding our path forward. This awareness could precipitate an intervention sooner rather than later, before such an intervention becomes considerably more challenging or hazardous. Another significant indicator for external observers is climate change, essentially a reversal of terraforming. The degradation of a habitable planet due to industrial activities presents a picture of either profound ignorance or deliberate self-annihilation. In either case, it suggests a species struggling with planetary stewardship. Evaluating a civilization's readiness for interstellar expansion, observing its self-inflicted environmental instability, would be a grave concern, implying a propensity to replicate such errors on other worlds or within other systems, thus propagating the problem. Alternatively, it might signify an impending crisis that will either lead to extinction or necessitate rapid, fundamental adaptation, with the outcome dictating the nature of their future interactions. The recent global disruption caused by a respiratory virus from 2019 to 2023 also serves as a critical data point. Our collective response was characterized by chaos, politicization, and a distressing lack of international coordination. While some nations navigated the crisis adeptly, others faced catastrophic failures. For any civilization assessing humanity's capacity to confront existential threats, the pandemic represented a crucial, real-time test, and our performance was decidedly mixed. The unprecedented speed at which vaccines were developed is undeniably impressive. However, this was counterbalanced by a significant portion of the population rejecting these life-saving measures due to unfounded conspiracy theories, governments prioritizing economic concerns over public health, and a prevailing spirit of international competition over genuine cooperation. From an external vantage point, this scenario depicts a species possessing the means to avert disaster, yet demonstrating an apparent inability to utilize those means effectively. This is highly diagnostic information for predicting our future trajectory. The question of why now can be answered through a multitude of possibilities. Perhaps it's because we've become detectable, because we've entered a critical phase of the Great Filter due to our burgeoning AI development, our climate destabilization, or the revelation of our coordination failures during the recent pandemic. It could be our specific location within the galaxy at this particular temporal juncture, a routine survey mission coinciding with our technological emergence, or even an unforeseen factor, something mundane to us but profoundly significant to them, that has captured attention. The unpredictability of non-human intelligences means we cannot anticipate what they will deem important. Trivial matters to us might hold immense weight for them, while issues we consider critical could be dismissed. However, if forced to speculate on the most probable reason for an extraterrestrial probe's arrival at Earth in the specific year of 2025, I would posit it lies in the confluence of our capabilities and vulnerabilities. We are sufficiently advanced to be of interest, possessing spaceflight, nuclear technology, and sophisticated computing. Yet, we remain vulnerable enough to be manageable. Our confinement to a single planet, our political fragmentation, and the limited scope of our weapons relative to interstellar scales render us susceptible. We exist within a narrow window of peak observability, conspicuous from afar but not yet possessing the sophistication to conceal ourselves or mount an effective defense. This window of opportunity may be brief, perhaps spanning a few centuries between becoming detectable and either perishing or achieving a level of advancement that deters casual approach. For any civilization seeking to observe, interact with, or assess another developing species, this precise window is the opportune moment, and for humanity that moment is now. We are demonstrably present, highly visible, undergoing rapid transformation, and showing no signs of imminent departure. This combination makes us an ideal subject for reconnaissance. If the three-body probe is indeed a reconnaissance mission, then the assessment process is already well underway. They are not querying why now. They are meticulously documenting our present state. We are, in essence, performing for unseen judges, being evaluated by unknown standards, and facing consequences beyond our comprehension. This is what renders 2025 particularly significant, not due to any deliberate choice on our part, but because this is the year we became sufficiently noteworthy to warrant such a journey. The dark forest, where silence signifies peril. A particular passage in Liu Cixin's science fiction novel, The Three-Body Problem, profoundly reshaped many perspectives on alien contact. It's known as the dark forest theory, and it posits the following. The universe resembles a vast dark forest. Every civilization is an armed hunter, moving stealthily through the trees, striving for absolute quiet because every other inhabitant is similarly armed, also hunting, and the first to betray its presence risks immediate elimination. Within this paradigm, the absence of detected alien civilizations is not indicative of their rarity, but rather of the survival strategy of successful ones. They remain concealed. These civilizations understand that announcing their existence, revealing their location, or broadcasting their capabilities is tantamount to self-destruction. This is because somewhere in that cosmic darkness, a more powerful entity is listening, poised to eliminate potential threats before they can mature. This is a profoundly bleak outlook, predicated on the assumption that intercivilizational cooperation is either impossible or so fraught with peril that absolute silence becomes the dominant, most rational strategy. It offers a compelling explanation for the Fermi paradox, the perplexing question of why we have found no evidence of extraterrestrial life despite the universe's immense age and scale. According to the tenets of the dark forest theory, the reason for this silence is that every civilization that has revealed itself has ultimately been eradicated. Those that have endured have learned to remain hidden, to listen without transmitting, and to preemptively eliminate others before facing the same fate. This represents cosmic game theory taken to its most extreme and chilling conclusion. Now, let's apply this framework to the three-body probe. If the dark forest theory accurately reflects the universe's operational principles, then an interstellar object approaching our solar system is not an act of exploration, but rather reconnaissance preceding an extermination. The motivation for visiting another civilization is not curiosity, but rather to ascertain whether they pose a threat. If they are perceived as a threat or have the potential to become one, the logical course of action is to neutralize that threat while it remains manageable. This is the very logic that Liu referenced when he, alongside Heiss and Kra, alluded to the dark forest in their paper. They were not necessarily endorsing the theory outright, but acknowledging it as a plausible scenario that demands serious consideration, especially when contemplating the artificial origins of the three-body probe. The strategic reasoning is chillingly pragmatic. For a spacefaring civilization, detecting another developing species within its galactic sector precipitates a critical decision-making process. Option 1. Inaction. Ignore them, hoping they remain confined to their home system and pose no threat. This approach is inherently risky as civilizations evolve unpredictably. Those appearing rudimentary now could experience rapid technological leaps, accelerate their expansion, and emerge as competitors or threats within unexpectedly short time frames. Option 2. Engagement. Initiate contact, attempt to foster cooperation, establish communication, and pursue mutual benefit. This represents the optimistic pathway, but it hinges on a foundation of trust. By engaging, one exposes oneself, revealing one's location and capabilities. Should the other party prove hostile or become so later, invaluable targeting information has been divulged. Option 3. The dark forest approach. Execute a preemptive strike while the target remains vulnerable. This strategy eschews waiting for the civilization to achieve spacefaring status or develop weapons capable of posing a threat. Instead, it targets them while they are planet-bound, their technology rudimentary, and their capacity for meaningful resistance negligible. This is not motivated by malice or a desire for genocide, but by preventive security, neutralizing a potential future threat before it materializes. From certain game theoretic standpoints, this is the optimal strategy. When the stakes of misjudgment regarding another civilization's intentions are existential, the margin for error is vanishingly small. It is deemed more prudent to eliminate 1,000 harmless civilizations than to permit one dangerous one to flourish. This logic is abhorrent by human moral standards, which we would likely categorize as paranoid, evil, and utterly unjustifiable. However, human ethics have evolved within a context where the most severe potential conflict was tribal warfare or regional conflicts, terrible as they were, but not species-level extinction events. Our ethical frameworks are not optimized for scenarios where a single miscalculation could result in the annihilation of our entire species. A civilization that has endured for millions of years has likely encountered circumstances that have indelibly taught it the severe cost of excessive trust, delayed action, or adhering to moral principles that lead to destruction. Civilizational evolution, much like biological evolution, is subject to natural selection. Those with effective survival strategies are the ones that persist. If preemptive annihilation proves more advantageous for survival than trust, then the civilizations we are likely to encounter will be those that have thoroughly assimilated this lesson. Therefore, what might a preemptive strike against a planet entail? Direct kinetic weaponry, such as colossal asteroids accelerated to relativistic speeds to sterilize the surface, would likely be deemed inefficient. Such an approach would result in the destruction of infrastructure and rendering the planet uninhabitable, thus negating its potential utility. A more refined method would be preferable. Biological weapons, such as engineered pathogens specifically designed to target the dominant species while leaving the broader ecosystem intact, present a viable option. Released from orbit, these agents could spread rapidly, leading to a population collapse. Subsequently, the planet could be claimed without the mess and destruction associated with bombardment. Alternatively, nanotechnology, comprising self-replicating machines capable of deconstructing the threat at a molecular level, could be employed. This approach is considerably more difficult to counter, as the nanomachines would be ubiquitous, and conventional weaponry would prove ineffective. Another strategy involves not outright destruction, but permanent incapacitation. This could entail disabling their satellites, power grids, and communication networks, effectively regressing them to a pre-industrial state. In this scenario, they would cease to pose a threat, unable to reach space, project power, or undertake any significant action beyond mere survival on a devastated world. Monitoring systems might be deployed to ensure they never regain their technological prowess. This would essentially constitute a prison planet scenario, where the civilization persists but is technologically neutered and locked in stasis, with an external power maintaining control. Arguably, this approach is more humane than extinction, yet it still represents the termination of any meaningful future for that species. The crucial question remains whether such an action would be preceded by an announcement or executed without warning. Announcing one's intentions carries strategic disadvantages, affording the target time to prepare, react, and potentially inflict damage before the strike is completed. However, it also offers benefits. If the threat level is uncertain, and the objective is to assess capability and intent before committing to elimination, a preliminary probe might be deployed. Observing the target's reaction to the probe's presence, whether they attempt communication, destruction, or complete indifference, provides invaluable data for calibrating subsequent actions. The three-body probe, if indeed a reconnaissance device, might serve precisely this purpose. Its approach is detectable, yet not overtly aggressive. It does not accelerate towards us, nor does it transmit unambiguous threatening signals, merely navigating the solar system on a trajectory that brings it in proximity to major celestial bodies. Our response, ignoring it, would signal either obliviousness or disinterest. Observing without interfering would suggest awareness coupled with passivity or caution. Attempting interception or destruction would indicate aggression and a perception of threat, along with a willingness to engage kinetically with unknown objects. All these reactions furnish data points about our nature, capabilities, and threat level. Based on this gathered intelligence, critical decisions regarding future actions will be made. Liu's analogy of a blind date where one fears encountering a serial killer is remarkably apt. When the intentions of the other party are unknown and unpredictable, vigilance for warning signs becomes paramount. From an extraterrestrial perspective, humanity presents a plethora of such warning signs. Our history is replete with interhuman aggression, characterized by constant warfare and pervasive violence. We exhibit aggression towards other species, having driven countless to extinction, and routinely exploit and degrade ecosystems for short-term gain. We have developed and deployed weapons of mass destruction, including conducting hundreds of nuclear tests with full knowledge of the detrimental effects of radiation fallout. Our political landscape is unstable, fragmented into competing nations that struggle to coordinate even on existential issues like climate change and pandemics. Consequently, the evidence does not paint a flattering picture when assessing whether humanity would be a responsible galactic neighbor. However, there is also counter-evidence. We are capable of creating art, music, literature, and beauty for its own sake. We have individuals and groups dedicated to preservation, conservation, and the pursuit of peace. We have established international laws and norms that, on occasion, prove effective. Our journey to the moon was marked by a plaque proclaiming our arrival in peace for all mankind. The Voyager spacecraft carried golden records, intended as a form of communication for any civilization that might encounter them. We are a species of contradictions, certainly, but these contradictions encompass genuine impulses toward cooperation and exploration, not solely conquest. Whether this inherent duality is sufficient to counterbalance the manifold warning signs is the crux of the assessment. The dark forest scenario is deeply unsettling because it offers no viable defense. If a civilization millions of years our senior perceives us as a threat, resistance would be futile. Our entire arsenal, every conceivable defensive measure, would be rendered irrelevant against technology of such vastly superior advancement. The disparity would be akin to Bronze Age humans attempting to combat a modern military force. The gap in capability is so immense that any attempt at resistance would be meaningless. Our sole hope in such a catastrophic scenario rests on the possibility that our assessment of their intentions is flawed, that the dark forest logic does not apply, and that they are benevolent or, at the very least, indifferent, rather than preemptively hostile. However, hope is not a strategy. If one is planning for the worst-case scenario, contemplating humanity's response to the three-body probe representing such a threat, the stark reality emerges that there is nothing effectively we can do. One could advocate for attempting to disappear, ceasing all broadcasts, and eliminating electromagnetic emissions to become effectively dark, in the hope of avoiding detection or being deemed not worth the effort. However, we have been broadcasting signals for a century. These emissions have already propagated outward. They cannot be recalled. Even if we were to cease transmissions immediately, our artificial illumination remains visible, and our atmospheric composition bears the indelible marks of industrial civilization. The evidence of our existence as an industrial civilization cannot be erased. The only outcome of going dark would be to render ourselves more vulnerable to any other observers who notice our cessation of transmission and subsequently inquire about the cause. This could be interpreted as either a societal collapse or a deliberate adoption of stealth tactics, potentially suggesting hostile intent. Another proposed strategy involves accelerating our space development, establishing off-world colonies on Mars, the Moon, and asteroids, thereby distributing the species and mitigating the vulnerability of being confined to a single planet. This is a sound, long-term survival strategy in any case. However, the establishment of self-sufficient off-world populations takes decades, perhaps even centuries. If the three-body probe signifies an immediate threat, with probes potentially arriving in December, we simply do not have this temporal luxury. It would be akin to ants attempting to construct new mounds while a magnifying glass is already focused upon them. Yet another approach is to attempt communication, endeavoring to demonstrate that we are not a threat, that we possess intrinsic value beyond mere elimination, and that we are worth preserving. But what would we say? How can we convincingly assert our peaceful intentions when our history overwhelmingly suggests otherwise? How can we pledge that we will not become a future threat when our own developmental trajectory is so inherently unstable and unpredictable? Communication might foster dialogue and create space for negotiation, or it could inadvertently confirm pre-existing suspicions that we are sentient enough to be dangerous, communicative enough to potentially coordinate with others, and therefore warrant decisive action. The most chilling interpretation of the dark forest logic is that by the time we begin posing these questions, it is already far too late. The reconnaissance likely occurred years, even decades prior. The decision was rendered before we were even aware of being evaluated, and the strike is already in motion, en route. We would not be negotiating our survival. We would be awaiting an execution order that has already been issued. The three-body probe reaches perihelion, deploys its auxiliary probes, and these are not equipped with mere sensors. They carry payloads, weapons, nanotech, kinetic impactors, or some other means designed for efficient threat neutralization. We would discover this grim reality in December, upon the probe's arrival. It would not be first contact, but rather final contact. The dark forest would strike, and another clearing in the cosmic woods would open where a demonstrably noisy civilization once existed. I do not personally subscribe to this dire outcome. The evidence does not currently support an imminent attack. The trajectory of the three-body probe, its behavior, and the conspicuous absence of overt weaponization do not strongly indicate hostile intent. However, the purpose of contemplating dark forest scenarios is not to predict the future with certainty, but to comprehend the worst-case possibilities, thereby avoiding being caught entirely off guard should they materialize. The absolute worst-case scenario is that Liu is correct about the probe's artificial origin, but mistaken about all other aspects. This encounter would not be an act of exploration, scientific inquiry, or even an assessment for potential future cooperation. Instead, it would represent the hunter in the dark forest meticulously lining up a shot, with humanity positioned as the target that simply made too much noise.